In this video, we're going to take a brief look at what do we do when our function is piecewise and we have to evaluate certain limits, right? Well, building on what we did previously with algebraic functions, you would think maybe we just kind of, plug it in maybe into the right piece of the function, and then if we get a number, that would be our answer. The problem is that procedure, that algebraic procedure, only works for elementary functions, and piecewise functions are not considered elementary, right? So, it's an important note that piecewise functions are not elementary functions. So we can't categorize them or treat them the same way like if we had just like a basic polynomial or a polynomial times a trigonometric function. Because they're broken up into different pieces for certain subsets of their domain, they're not considered elementary. So plugging in doesn't always work, and we'll see through some examples, right? All right, so let's go through some examples, and we'll start with this one. So say my function is something like this. Let's just say it's a polynomial here whenever x is greater than or equal to 0, and then let's say it's a rational function like x plus 1 over x minus 5 when x is less than 0, right? So this is our piecewise function, and let's say we had to find the limit as x approaches 0, the two-sided limit of this function. So what is this, right? The difficulty or the problem that piecewise functions possibly pose is that the value of x, especially in the case of a two-sided limit, the value of x that is being approached might be the value of x where the function switches from one form or one type to another, right? So like, in other words, whenever x is greater than 0, right, it's gonna be the like this parabola would be the representation of the function, as opposed to when x is less than 0, then it's this rational function that would be the representation of the function. So whenever the key thing for piecewise functions is if your value of x that is being approached is a value of x at which the function changes from one piece to the next, we have to utilize the one-sided limits, right? So we first have to say, even if the question doesn't ask us to do the limit as x approaches 0 plus or 0 minus, we have to know to do that because they're two separate functions here. So the limit as x approaches 0 from the positive side, right? Well, that would be evaluating this. So I'm going to write, so this piece, this would be the limit as x approaches 0 plus of the polynomial, x squared minus x plus 1, right? And that's because this is how f of x is defined when x is greater than 0. And that's what this notation means, right? And then I can use what we previously did and say, well, this piece happens to be a polynomial. So I can try to plug 0 in, right? And when you do that, again, and we talked about it with the polynomial evaluating at 0, all you're going to be left with is the constant term, if there is one. Well, there's always a constant term. You can think of it as a plus 0 if it's missing. But that's equal to 1. All right. So that's the limit of our piecewise function from the right as x approaches 0. Well, what does it look like from the left? Again, because it's now a different function, we have to do another limit evaluation, right? So it's almost like we have to evaluate the two pieces that are used when our value of x in this case is, or x is getting closer and closer to 0. We have to evaluate the two pieces, right? And then see if they're the same, right? And let's see. So the limit as x approaches 0 minus, it would be of this, the rational function, your x plus 1 over x minus 5, plug 0 in, the numerator gives me a positive 1, the denominator gives me a negative 5, so that's a negative 1/5, right? So we have one-sided limits, right? The limit from the right is equal to 1, the limit from the left is equal to negative 1/5, but because these are not equal, what this means is that the two-sided limit does not exist, right? So I'll say this, so since the limit from the right of f of x is not equal to the limit from the left of f of x, the two-sided limit, so the limit as x approaches 0 of f of x does not exist, right? So we can't just plug it in, and this goes back to some previous work that we did. I just want to make a little note. So even though the two-sided limit doesn't exist, we do have a function value. So I'm just going to say note. We could plug 0 in, and if you're plugging 0 into this piecewise function, you'd have to use the top piece because that's where the equal sign is, right? So when x is greater than or equal to 0, you'd have to use the polynomial, which in this case evaluates to 1, right? So we do have a function value, but no two-sided limit, right? So the function value exists, but not the two-sided limit. And that's, again, another important concept. So with these piecewise functions, you can't just plug in one time and say, oh, I got a number, and that's it. All right, let's do another example, maybe a piecewise function where there are 3 pieces to the function. Man, we're getting brave here. So let's call it g of x, mix it up. So let's say it's 1 minus x when x is less than negative 2. And then let's say it's x squared plus 1 when x is greater than or equal to negative 2, but then let's say less than 1. And then let's say, what do we have here? Let's say x minus 1 squared plus 2 when x is greater than or equal to 1. All right. So yeah, here we have it's one function that's piecewise, and here are the subsets of the domain. So notice I use polynomials all the way through, right? So we know polynomials are defined everywhere, but you only use the top piece when your x is less than negative 2. You only use the middle piece when x is greater than or equal to negative 2, but strictly less than 1. And then you only use the bottom piece, the third piece, when x is greater than or equal to 1. All right, so let's find the two-sided, well, let's see, does this two-sided limit of g of x as x approaches negative 2, does that exist? So for negative 2, now at negative 2, the function changes from the linear function here to this parabola, right? So again, since it's piecewise, we have to consider the one-sided limits. And let me just write them down here. These are the two things that we have to consider, even if the question doesn't specifically ask us to do so. How do we know? Because the function is piecewise. So we have to be able to recognize our piecewise function and know that if x is approaching one of these, I guess you could call endpoints of the subset of the domain, then we have to split it into the right and left-sided limits. So let's see, when x is greater than -2, but close to -2, then you would be in the middle piece. So then we would have to use the x squared plus 1. So this is the limit as x approaches -2 plus of x squared plus 1. And again, now that piece itself is a polynomial, so we know we can plug it in. So we will have -2 squared plus 1. Order of operations, -2 squared is 4, plus 1 is 5, right? Similarly, which piece do we use when x is less than -2? That's what this minus sign here is telling me. Well, that means I'd have to use the top piece of the function. So this is the limit as x approaches -2 minus of the quantity 1 minus x. Again, a linear function is a special case of a polynomial. We plug it in, and we end up with 1 minus -2, and that's 3. So the one-sided limits are different. So this two-sided limit does not exist. All right. Let's do the other one really of interest, and that's what happens as x gets close to 1. So let's repeat this process. And now look at the two-sided limit of g of x as x approaches 1. What is that equal to? Well, again, we have to split it up. We have to see, what happens to the individual pieces. So the limit as x approaches 1, let's say plus, of g of x, what piece do we use when x is bigger than 1? Well, that's the bottom piece. Right, so limit as x approaches 1 plus of the quantity x minus 1 squared plus 2. Well, plug 1, so you have you have 1 minus 1 squared plus 2, that's 0 squared, that's 0 plus 2, so that's equal to 2. What about the limit as x approaches 1 minus of g of x? Well, what piece is this? So this is saying, remember the 1 with the minus at as a superscript is saying that x is less than 1 but very close to 1. And that means you would be in this interval, so you'd have to use this piece of the function. So we have the limit as x approaches 1 minus, and then we're using the middle piece again. So you see, like, the middle piece shows up twice. Why does it show up twice? Well, because there are two values of x, right? Two endpoints. So as it switches from -2, less than -2 to greater than -2, you use this piece. Similarly, as it switches from being less than 1 to greater than 1, again, you'd use these two pieces, right? So let's evaluate this. So we have 1 squared plus 1, that's equal to 2. Okay, so now we have an instance where the two one-sided limits are the same. So from either direction, right? And these are two different parabolas, mind you, but somehow the two-sided limit is going to be equal to 2. So the limit as x approaches 1 of g of x, that's equal to 2. right? So this is a good example. It shows you, with the piecewise functions, that you have to be able to determine when you need to split and check the one-sided limits. Let's do a third one, not a different piecewise function, same piecewise function, but just a different limit, not -2 or 1. So what if the question is, what is the limit as x approaches 5 of this function? Well, when x is approaching 5, right, there is no break in the function, right? The function, let me go back up again so you can see it. The function changes pieces, quote unquote, at x equals -2 and then at x equals 1, right? At x equals 5, there is no change because 5 is greater than 1. So whether you're coming from the left or coming from the right, as you approach 5, you're going to be using this piece of the function, the x minus 1 quantity squared plus 2. So there's no need to split this up, right? Because the function doesn't change form at x equals 5. It doesn't change from one piece to the next. It's essentially one piece of the function. So this is the limit as x approaches 5 of the quantity x minus 1 squared plus 2. And then here we plug it in, again, using our fact that this piece itself is an elementary function. And we get 5 minus 1 squared plus 2. So this is 4 squared plus 2. That's 16 plus 2. That's 18, right? So again, with piecewise functions, looking at the domain and seeing where the function changes from one form to the next or one piece to the next, that will determine whether or not you have to split the two-sided limit into the two one-sided limits, or if you can just evaluate by plugging in, right? So important concepts here. Definitely think about it. Maybe watch the video again, maybe do the problems on your own, and hopefully you're on your way to mastering this concept. See you in the next video.